one thing that I wanted to talk a little bit more now was to take us a little bit further in model construction. So we had spent some time on the first day looking at the general linear model and how you construct covariates to model effects in the data. And I want to talk a little bit about covariates of no interest now, as sort of another component of a statistical model. So we established that in our prototypical bagel donut experiment that you might have some data that looks like this. Right? And we also further established that we could create covariates corresponding to the donut effect and the bagel effect. Right? And we figured out that we could have beta values to kind of scale these up or down to fit it. And we further established that what you can do is if you then look at the difference between, I'm going to draw in orange now the fitted data, or the model. That if you look at the difference between the model and the data, you get the residuals, or the error term, which looks something like that. Okay, they should be, if the model is well composed, it should be the case that the error values are random, are independently and normally distributed. In fact, that's an assumption of parametric models, is that these error terms here, if you look at the distribution of those values, they're normally distributed and they're independent. And actually, when we were talking about the 1 over f noise, one way that is manifest is that if you don't correct for the 1 over f noise, you find that these error terms, these residuals, are not independently distributed. They're distributed with this 1 over f thing. So one way that or one sort of demonstration of the fact that the corrections that we perform in our statistical modeling is appropriate is that we find that when you take a look at the residual terms from one of these more modern statistical analyses of bold fMRI data, you come up with errors which are independent and normally distributed, which is just as they should be. Okay, well, at least that's generally how it is. Sometimes, if you take a look at the error terms, you'll find that there are effects there which render the residual terms not independent and normally distributed. And so this is the case in which there are further sort of effects or confounds present in the data which are not well modeled by your task covariates. So let's talk about those a little bit. So in the example we've given so far, we've got some data and we've got two covariates which are modeling changes in neuronal activity that we expect. We know it's possible that there are things that influence the bold fMRI signal beyond just the particular experimental effect that you introduce, right? Whether you present pictures of bagels and pictures of donuts. What are some other things that might affect the bold fMRI signal? Well, let's see. So we know the bold fMRI signal is a result of a rather complicated interconnected chain of events, including changes in blood flow, changes in physics and physiology, signal changes in T2 star and all the rest. So perhaps that there are influences at those levels which can make changes in the signal which are not really just the result of neuronal activity. So what are some of those? Well, let's suppose, for example, that the caliber of blood vessels in the brain is affected by the ambient temperature in the room. Right? It's possible that's the case. Right? So, for example, actually, it's probably not possible it's the case, but let's just work with this ridiculous example. Let's suppose it's the case like when you're in a very cold room, there's like vasoconstriction and all your blood vessels clamp down on the periphery, so there's more blood that's delivered up to the brain as a consequence. Let's just suppose. So blood flow increases to the brain when the room is cold and decreases to the brain when the room is hot, which is why when it's rather hot outside and you're laying on a beach, you're all languid and sleepy. So let's suppose. And then let's further imagine that you run a few experiments and you analyze your data, and your trusty graduate student who has managed to hold on to their position in your lab despite the projector bulb burnout fiasco comes to you and says, I've noticed that actually the temperature in the scanner room seems to fluctuate an awful lot during the course of the experiment. You say, oh yes, really? They say, yeah, and I've made some measurements, and it goes something like this. When I take a look at the at a graph of temperature over time in the scanner, it goes something like this. It rises and rises and rises and rises, and I guess an air conditioner kicks on or something, because it then drops and then comes back down again for a while. Okay, and so this is a graph of temperature. And I've been looking at our bold fMRI data, and I think I can see the effect of temperature in the data, because it looks something like this. On top of our predicted effect, which is the true neuronal activity effect that looks like this, there's superimposed on top of it this kind of effect. Right? So you can say, oh, look at that. Yeah, as the temperature goes up, the bold fMRI signal decreases, and as the temperature, and then with this drop, it starts to change and go the other way or something. Right? It should have to go like that to make sense. Yeah. So anyway, there's some effect, right, that we can see some relationship between temperature and the data that we acquire. Okay. Well, if we don't try and do something to correct the data for this effect, our statistical model, the best that our little model is going to be able to do, isn't so great. So like this will be the attempt of the statistical model to model the donut effect, right? And this will be the attempt of the statistical model to model the bagel effect, right? These are constrained to modeling these kind of straight line effects. But obviously, there's some kind of waviness that's going on in the data that's the result of temperature. So how could we correct for this? Well, luckily, what you can do is introduce another covariate into the data, which is simply this thing, right? Which is your measurement of temperature over time. Include that as yet another covariate in the model. So this covariate now, well, in effect, you're going to actually have to flip this thing upside down to fit the data. But so this would kind of, come in here and model the data, something like, I don't know, something like that. And as a consequence, then, this variability in the data would be explained. And so if you start to add together the different covariates we have, you would then end up with a composite covariate of both the covariates of interest and then also this nuisance covariate of temperature. So if the total model fit would look something like this, right? Which is doing a lot better than each individual covariate was doing on its own. Okay, so everybody understand at least that general principle, right? So if you have an effect that's in your data that you can model with a covariate, then you include it and explains that variability in the data and then improves the overall fit of your model. Okay? So temperature is sort of a facetious example. What are some real examples of stuff that might turn up and that we'd want to include in our analysis of the data? Well, a very common one is global signal. All right, so what's global signal? Well, the notion of global signal dates back to the days when people were analyzing PET data, okay? And what they'd observe is that you can measure a global cerebral blood flow, like what is the blood flow to the entire brain, right, over the course of an experiment. And they'd find that that would fluctuate over time. And really their interest was in local changes in neuronal activity as divorced from entire global changes in blood flow, right? So in the temperature example, that was one thing that was changing global blood flow. All the blood flow to the brain decreased as it got warmer and then increased as it got colder, right? And what we're interested in are local changes in neuronal activity that are superimposed on those global changes. So one thing that people had suggested from early on was to try and obtain a measure of the global blood flow and then include that as a covariate. Because there's lots of things that might influence global blood flow. Heart rate, respiration, ambient temperature in the room, level of arousal, sleepiness, all sorts of things like that. So the tactic that's employed then is to say, well, if here's my data over time, just simply take the time series, right? So you can take the time series from one voxel here, right? And that gives you, there's some time series data, and then take the time series from another voxel, and average them all together. Get the average time series from across the whole brain during the course of the experiment, okay? And call that thing the global signal. Okay. And then you then include that as a covariate in your analysis to take into account these sort of global changes in blood flow that accompany respiration and heart rate and all the rest, okay? So this is routinely done, all right? There is one potential problem, though, and that problem is the following. If there isn't too much of a global change in blood flow, but there is a very big local change in blood flow that's a consequence of your experimental effect, then the global signal is going to look an awful lot like your task effect. Right? So imagine that, for the most part, the brain was a fairly quiescent place, except when you were flashing lights for 30 seconds and it was dark, and then flashing lights for 30 seconds and then it was dark. If you average together all the voxels, the global signal that you see might reflect that on and off of flashing the lights. Okay? So then you're now including a covariate which looks an awful lot like your task covariate. Okay? They look basically the same. In that case, then, this global signal covariate is now acting as a confound. So let me explain real quickly this hierarchy of different kinds of covariates of no interest. In fact, let me take a step back and explain what a covariate of no interest is. So we've talked about so far covariates of interest, which are these covariates which are modeling experimental effects about which we wish to make test hypotheses and write papers and publish stuff in science. Okay? Those are covariates of interest. Covariates of no interest are covariates that are modeling variability or variance in the data that we don't have any hypotheses about. We would be just as happy if that variance didn't exist, if it wasn't there in the data to begin with. Okay? We don't want to test any hypothesis about it, so we're going to model it with a covariate to try and take it away. Now, it turns out, as far as the general linear model is concerned, it doesn't give a hoot whether or not a covariate is of interest or of no interest, right? That's your problem, not the general linear model's problem. It's going to treat all these covariates identically, all right? And it's just kind of the stance that you adopt towards their interpretation, right? In fact, it could easily be the case that for one person, a covariate is of no interest, and for another person, a covariate is of quite a bit of interest, okay? And so different experimenters might bring different interpretations to covariates. But then covariates of no interest can be further divided into nuisance covariates and confounds. So a nuisance covariate is a covariate that doesn't have any relationship to your task whatsoever. Bears no correlation to your task. All right, so there's no way that the variability that's introduced by the nuisance effect could ever be confused for your task effect. On the other hand, a confound is a source of variability in your data which is not of interest, yet just so happens to be correlated with your task. Okay? It confounds your task. It makes it difficult for you, the experimenter, and for the statistical model to distinguish between what was the effect of your task and what was the effect of this nuisance thing that you're not really interested in, this confound. And a global signal covariate fits that definition of being a confound under some circumstances. If it's correlated with your task, you can't really know whether or not any variability that you see in a single voxel should be explained by the global signal covariate or by your task. Okay? And as a consequence, what that means is that the inclusion of confounds, of covariates which tend to correlate with your task, will tend to decrease the experimental effect that you measure. Because again, the statistical model can't figure out how I should assign the variance. Should it go to your task or should it go to this confound? So the overall significance of the effects are decreased. In fact, if you include global signal covariates, which are strongly correlated with your task, you can actually take effects and kind of turn them the opposite way. So if you have a region of the brain that has a weak task effect, okay, in fact has a task effect which is less than that seen in the global signal, then the best interpretation the model can do is say that your task had a negative effect in that voxel as compared to the global signal. And so you'll turn a positive t-value into a negative t-value if you include a global signal under those circumstances. Okay? So all that being said, use global signal covariates with caution. If you include one, it's important that you evaluate whether or not the global signal covariate is actually correlated with your task. And within VoxBo, there's a little menu option that allows you to do that. You just drop down Evaluate Collinearity with Interest, it's called. And it will give you basically an R value, or a correlation value, where 0 is not correlated at all and 1 is perfectly correlated. They're identical, boss. You can see how similar your global signal covariate is to your experimental covariates of interest. And in general, if it's greater than about 0.3, then maybe you should think about not including it. Okay? But that's just a rule of thumb. There's no absolute right or wrong answer to this. Okay? Global signal covariate. What are some other covariates of no interest that we generally include? Any other questions about global signal covariates before I talk about some others? Okay. Other sorts of covariates of no interest that we include things called scan effects. So a scan effect is just a covariate which models the difference in mean level of signal between one scan and the next. And so the reason we include that is because you'll often see bold fMRI data that looks like this. So here's your data from scan number 1, then here's your data from scan number 2, right? Scan 1 and then scan 2. So this often happens, and I'm told that the reason this is because the amplifiers on the scanner sort of reset between one scan and the next, and so we'll just change the overall level of signal. These are signal values which are about 1,000, and then for some reason now it's giving out signal values which are about 880, say, though it's generally not of that large magnitude. But anyway, so you can include covariates which model these scan effects that basically model a shift in the mean level of signal between one scan and the next. That's a scan effect covariate. That's another typical model covariate to include. Another sort of covariate that's often included is a movement covariate. We're going to talk about movement more on the last day of the session, but in general, head motion in the scanner can be a problem for bold fMRI experiments, and it can be fairly tricky to correct. We do data preprocessing to try and remove the effects of motion from our data, but those effects aren't, that correction is not perfect and not completely successful for reasons we'll discuss later on. So it is sometimes the case that you'll include covariates in your model which are modeling basically the subject's head motion over the course of the experiment. Okay? And those covariates are available because when we do our data preprocessing, as we'll talk about later on, what gets saved, among other things, is a vector, a file, which contains within it a measurement of how much the head was moving over the course of the scanning experiment. And you then include that as a covariate in the model to then remove any effects from the data, which could be explained by the subject just rocking their head back and forth. Again, that's another place where you have to look to see, is your movement covariate actually acting as a confound? Is it correlated with your task? Because it might be the case that, if you have someone, during, for 30 seconds they rest, and then for 30 seconds they have to do bilateral flexing arm movements while yelling and screaming, right? You're going to see much more movement during the on condition than during the off condition. So you might tend to see a lot of movement during that period and then no movement during the other period. In that case, then, you'd find there's a strong correlation between your movement-related covariate and your task covariates. And in that case, you'd probably want to ask whether or not this is really data you want to analyze and publish. I'm serious, because if there's a very strong correlation between your movement covariates and your data, then you're going to have a very hard time saying what was movement and what was task. Okay. So that's about it for nuisance covariates and covariates of no interest. There are others. Yeah. Oh, trial effects. Yeah. So it's similar in concept to a scan effect, and it's just so the question regards trial effects. So in what are called sparse event-related design experiments, which we'll be talking about in just 2 minutes, you might have fMRI data that looks like this. Let me try to make that a little bit tighter. So you have data which, the original data, say, was supposed to look like this, where you've got an event every 16 seconds. This was neural activity that looked like this, right? Every 16 seconds they saw a picture of something or, made some kind of response or something. But then the data that you actually record looks like this. Right, where there's, for some reason, some fluctuation in the baseline from one trial to the next. And so a trial effect covariate is one that is a covariate that looks like this, or a set of covariates, I should say, that look like this. Right, where they have the effect of modeling the mean level of signal during each of these trials and removing it. Okay, so it basically takes each trial and kind of realigns them to be on an even keel, and so then you can compare their deviations from the baseline, sort of from an even starting point. No, they'd be redundant. So if you include trial effects, you wouldn't want to include scan effects. Yeah. Yeah.
Are any of these effects attenuated with filtering?
Filtering. So filtering, what kind of filtering?
Filtering we were talking about earlier.
Like removing low frequency effects? Yeah, so it turns out that, for example, scan effects are largely, taken care of by doing low frequency filtering, but not perfectly. And same thing with trial effects. Largely taken care of by filtering, but not perfectly. But nonetheless, we include them because we've got so many degrees of freedom to spend. Why not try and come up with a perfect model? Yeah?
Is there a risk of inadvertent effect by doing within trial?
Well, it's possible. And in fact, there's a whole class of experiments now that try and distinguish between sustained versus transient changes in neuronal activity. And it might be the case that, during these trials, the subject was being asked to retrieve information about color. And during these trials, the subject was being asked to retrieve information about motion. And it might be the case that, while you're in the state of waiting for questions about color, you increase neuronal activity to some area of the brain. And while you're in the state of waiting for questions about motion, you increase neuronal activity to some other area of the brain. So it might be the case that, in reality, you should observe data that looks like this, where it's right, that might be a real effect, that there is not only a transient effect of each event, sort of an event that might be modeled like this, right? But then there's also sort of a sustained effect, which you could model like this, where there really is greater neuronal activity all throughout this period of time when you're seeing different trials. And these are referred to as transient and sustained effects, and there's experimental designs which attempt to model and detect those kinds of effects to answer cognitive neuroscientific questions. Yeah?
With the example looked at the global signal and the amplifier effect you gave.
Right.
Talk about the benefit of including those as nuisance covariates versus, say, trying to just scaling them out of the signal or subtracting them out of your signal.
Right, sort of like global signal effects? Yeah, so that's a classic example. So, boy, could I point you to a huge literature that you would find fascinating, perhaps. Maybe not. So this was a subject of debate, endless debate in the PET literature, which then carried over into fMRI. And it lasted for probably about 5 or 6 years. And it was, how should we model global signal effects? Should we scale them out as sort of a data preprocessing step, or should we try and model them using a covariate in the analysis, which is better? And in the end, it really doesn't make much difference. It just doesn't make much difference. And so it was sort of 100 papers battling over an insignificant difference in effect. So it doesn't matter which one you do. So some statistical packages do a scaling to remove the global signal. In fact, SPM99 did do scaling to remove the global signal. Now maybe they don't in SPM2. I don't even remember anymore. But it doesn't. It's 6 of one, half a dozen of the other. It doesn't matter which one you do. In that case, the other covariates, that might not be true. Yeah, so the question is there an upper bound to the number of nuisance covariates you can add? There is, the number of degrees of freedom you have. For every covariate you add, it costs you a degree of freedom. Okay? So you can keep adding in covariates to try and model nuisance effects in your data to try and perfectly tweak the effects to kind of just come out right. But every time you add a covariate, you spend a degree of freedom and reduce the overall significance of your result in the end. So the trick becomes, in adding covariates, is to add a covariate that pulls its weight. Right? You want to add a covariate of no interest that explains more variance than it costs you in a degree of freedom. Okay? And in fact, that's the original meaning of an F statistic. An F statistic is one that you use to ask, is a covariate explaining more variance than it would just by raw chance? Is it pulling its weight more than its degree of freedom would cost you? So there are ways, and when we talk about basis sets at some point, I'll talk about F statistics. There are ways of taking a look at your covariates of no interest and evaluating them with an F statistic to see if they're pulling their weight. But again, since in general we have so many degrees of freedom, it's not much of a concern. Okay? All right, so experimental design. So here we are, just shy of the halfway point of the course, and we're going to talk about experimental design. About time. Okay, so we've covered a lot of ground. We've figured out how it is that we can analyze fMRI data. And we've discussed a lot about the properties of bold fMRI data that might inform experimental design. We're familiar now with the hemodynamic response function and its filtering properties. And we're familiar with the 1/f noise characteristics of data and the effects that it has upon trying to detect slow changes in neuronal activity. So now you want to actually make an experiment. So what are some of the considerations that might play into designing an experiment? And I have to say, the way that I'm going to talk about this next section has been very much informed by a paper that I've recently read by some guys named Liu and Frank, which appeared in Neuroimage just a couple of months ago. And I think coalesced very nicely a few concepts that I'd been describing in perhaps more scattered terms previously. Okay, so what's the purpose of doing an fMRI experiment? Well, you're aiming to try and detect a change in neuronal activity that you introduce by your experimental design. Right? That's in the end what your goal is. So probably one of the top priorities that you might have for your experiment is detection power. So you want to be able to maximize your ability to detect a change in neuronal activity introduced by your experiment. So that's probably number one priority, detection power. What's another priority? Well, another thing that might be of interest to you is something called randomness. So now why is this important? So randomness refers to the ability of the subject to predict what the next component of the experiment is going to be presented. Okay? So thinking back to sort of the original sort of block designs that were initially developed for bold fMRI, this is where you have 30 seconds of one thing, 30 seconds of another thing. So in the original case, the way you designed these experiments, if you were interested in, for example, learning about memory, right? You'd have someone learn a list of words, and then you put them in the scanner, and for 30 seconds you'd show them words that they hadn't seen before, and for 30 seconds you'd show them words that they had seen before, and you'd ask them the question, have you seen this word before? Right? Every time you'd ask them, have you seen this word before? Well, if for 30 seconds you see words which you have seen before, and for 30 seconds you see new words, pretty quickly sort of the artifice of the experiment will become rather evident to the subject, right? It'll be like, oh, these are all words I saw before, now these are a bunch of new words. And so it becomes sort of this effortless action on the part of the subject, say like new word, new word, new word, old word, old word, new word, new word, new word, old word, old word. So it loses, in effect, the very effect that you're interested in. So it might be the case that one thing you're interested in is having some randomness to your design, so that the subject is not able to anticipate what the next trial is, so that new words or old words appear in an unpredictable manner. Okay? So this is another important component. And then finally, there's something called estimation efficiency, which we're not going to talk about too much. But this is referred to as, this is optimizing experimental design for the purposes of measuring the shape of the hemodynamic response function. Okay? Sometimes, under some circumstances, you might be interested in figuring out what the shape of the HRF is. All right? In general, we don't tend to do that too much in practice. All right? We've got a pretty good measure of what the average shape of the hemodynamic response function looks like across subjects. That work has been done. And unless you're doing some studies about physiology, in general, you're not too interested in trying to measure the shape of the HRF. Okay? But it turns out that, for example, these two things are, well, I'm sorry. These two things are sort of held at sort of opposite ends of the spectrum. That is, if you want to design an experiment which is very good at measuring the shape of the HRF, you have to have a fairly random sort of design. But if you have a design which is very unrandom, is very predictable in its design and shape, then it won't be very good at estimating the shape of the HRF. We won't get into great detail about that, but if anyone's interested in those details, we can go on later, or I can introduce you to papers which can describe it. But the main thing that's probably of interest here is the relationship between power and randomness. Okay? Maximizing your ability to detect an effect and also minimizing the ability of the subject to predict what comes next, right? And whether or not those things are important to you. So let's suppose the only thing that's important to you is power. You just want lots of detection power, and you don't care if the subject knows they're being manipulated or not. You just want power. Okay? So for that kind of design, randomness is not at all important to you. And in that case, the optimal kind of design is a blocked experiment. Okay? This is one that maximizes power. And the reason it does so is because, as we've seen before, an optimal fMRI experiment from the standpoint of detection power is a balance between the hemodynamic response function, right, getting a low enough frequency so that it passes through the hemodynamic response function, and yet keeping it high enough so that it doesn't run into all this like low noise down at the low frequency range of the noise spectrum. Okay? So it turns out that there's sort of an optimum trade-off between those two, where you have like just high frequency enough to avoid the noise and just low frequency enough to make it through the HRF. And so using a block design like this, you can position the experimental variance at just the right frequency to kind of pass through, you know, the rock and the hard place that you have to go through to kind of get your experimental variance detected at the other end. And so it turns out that just practically, if you have a blocked fMRI experiment that has blocks which are about 20 to 25 seconds in length, that's an optimal experiment from the standpoint of detection power. 25 seconds of one thing, 25 seconds of the other thing, alternate back and forth, you're golden. That is the most powerful bold fMRI experiment you can do, with the possible exception of, and I'll just mention it for completeness, a perfectly sinusoidal design, which would be even slightly better. But a blocked fMRI experiment with 20 seconds on, 25 seconds on, 25 seconds off is the optimal design from the standpoint of power. Okay. Now, of course, there's absolutely no randomness there. So every trial that follows is, you know, completely determined by the trials that preceded, subject to make complete predictions about that. Okay. Any questions about block designs? Okay. So now suppose, though, that you don't want optimal power, or you want to optimize power, but you also need a component of randomness. Okay. You need to have some ability to surprise your subject about what trial is going to come next. All right, well then, that opens us up to an entire family of different experimental designs that you can adopt. Let's take a look at one of the simplest just to begin with, which is a perfectly random design. Okay. So imagine that you're interested in just looking at the neural basis of flashing lights, right? You just want to be able to take a look at what area of the brain responds to a flash of light, but for reasons known only to yourself, you don't want the subject to be able to anticipate when the light is going to flash or not. So one thing you could imagine doing is presenting 2-second flashes of light, or 1-second flashes of light, and alternating those with periods of darkness. Okay? 1 second of light, 1 second of darkness. Now, we already know an experimental design that would be very bad, right? And that experimental design would look something like this. Flash of light, darkness, flash of light, darkness, flash of light, darkness, flash of light, darkness. So on, off, on, off, on, off, on, off with a 1-second alteration. Now, we know that that would be a very bad experimental design. Why? Well, as we've talked about it before, and from an intuitive standpoint, we said, well, you know, it's because the HRF couldn't keep up, and, you know, it would sort of rise, and you wouldn't be able to see, like, the on and off effect. But, you know, actually casting this in terms of a power spectrum argument, it should be quite evident. If you look at the power spectrum of something that's like this, it goes on, off every 1 second, the power spectrum, low frequencies, high frequencies, looks like this. Okay, there's the power spectrum of that thing. In fact, if it's 1 second on, 1 second off, and you acquire images at a rate of 1 second, this is actually the highest frequency. This is referred to as what's called the Nyquist frequency. It is the highest frequency that you could possibly have in the experiment. Okay? And as we know, the shape of the hemodynamic response function is such that it comes down like this, man, there is none of that variance is making it through to the other side, okay? That effect is going to be completely attenuated and removed. So that's why we, in a sense, know that this sort of design is going to be very poor. All right, so we can't do that, obviously. What about something else? Well, let's imagine if we took, suppose we had like 100 little flashes of light, each a second long, and we had 100 little periods of darkness, each a second long, and we just randomly assorted them together, right? We just put them all in a bag and kind of randomly picked out, is it going to be a flash of light or darkness on each trial, okay? And so then you had a design which looked something like this. Flash of light, dark, 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 flash of light, flash of light, flash of light, dark, 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 flash of light, dark, dark, or whatever. So some sort of random patterns of flashes of light and darkness, okay? How would this sort of design do? Well, you know, it's still the case that we have events which are kind of happening very briefly. It's just a second of light and then a second of darkness. But now they're randomly assorted. What's the power spectrum look like of something that's randomly assorted? Thinking back to channel 13, right, on my TV. Flat line, white noise. So the power spectrum of a completely random assortment of on and off lights is going to look something like this. Okay? So if this is the power spectrum of the hemodynamic response function, what's the power spectrum of the thing that finally results, the bold fMRI data that comes out the other side? Well, it's going to look just like this. It's just going to be a scaled version of the hemodynamic response function. Okay? In practice, if this is the neuronal activity, the bold fMRI signal that results from it is going to be some chaotic, like, you know, thing, right? Some chaotic, random, like up and down squiggly line pattern that's all smoothed out like that, right? And this just could look like complete noise, except it's your noise, okay? It's your pattern of noise that you made. You made this one particular pattern of all the possible patterns of noise that could have occurred. You created this one experimental pattern of like random variation, okay? And so if you go looking for this one random pattern of variation and find it, then you can have some confidence that it's an effect of your task, okay? So this is how these randomized, this is sometimes referred to as a rapid event-related design, okay? This is one in which you have lots of trials, they're randomly assorted, they come at you pretty quick. And what in effect you're doing is you're detecting kind of the low frequency envelope of these high frequency events. Right? You can't really detect any one event and differentiate it from a trial next to it, but you're detecting kind of like that low frequency, slow envelope of change that's associated with that design. Okay? This is a rapid event-related design, low frequency design. Okay? And so this is a sort of design which can certainly be used and is quite popular. Okay. Well, it turns out not all random designs are created equal. Okay? And the reason that is because it's possible that if you just choose a random assortment of values, you might not get a perfectly flat line power spectrum. In fact, you're unlikely to do so unless you have an infinitely long series of an experiment. The actual power spectrum that's associated with a random ordering of events that you pick is going to be something other than a perfectly flat white line. It's going to be, something like, who knows, something like this. Right? It's going to be something other than perfectly flat. Right? It's going to tend to be flat. So over 1,000 experiments, the average power spectrum would tend to be flat line. But any one is not going to be perfect. Which means then that different experimental designs, different random experimental designs, can differ in how good they are as a bold fMRI experiment, right? Let's imagine that you kind of put these all your blank periods and your flashes of light in the random bag, and you just pull them out randomly, and it just so happens that there was an incredible quirk of fate, and the random ordering that happened to get picked out was one that looked like this. I mean, people have been so unlucky. The Boston Red Sox managed to win this year. I mean, these things could happen, right? So it's possible that you could pull out the random assortment that happens to have a rather bad power spectrum from the standpoint of detection from bold fMRI. So not all random designs are created equal. And of course, this is an extreme example, but you can imagine examples where, for whatever reason, the way the trials came out randomly tended to favor higher frequencies over lower frequencies. So that's why there are techniques, or I should say algorithms, which allow you to kind of go through and generate a bunch of random designs and then evaluate them and say, like, well, how good a random design is this? Is it, how well does it do from the standpoint of being detectable by bold fMRI? And so there's a piece of software called OptSeq, which I think a number of you are familiar with now. It's installed on the CFN computers and over at the CCN as well. And this can be used to generate, so you basically provide the piece of software with some parameters about your experiment, how many trials you have, what are the different sorts of events you have. And then it'll go through and iteratively look at different random designs and pick out the ones for you which are better for the standpoint of being a bold fMRI experiment. Okay? And it turns out you can even do better than this. And so we start to get into a little bit more esoteric area. But recently we had a CFN discussion session where we talked about M-sequence designs. An M-sequence is basically a pseudo-random ordering of events which has the property of having a nearly flat power spectrum. Okay? So it's a way of artificially constructing a kind of random order of events which has this sort of optimal design. Okay? So it's possible to use this other thing, M-sequence, and there's software out there that gets there. In fact, if you run this opt-seq thing long enough, it'll arrive at the M-sequence solution. Yeah?
Something about this bothers me, though, that I mean, it seems like you don't really have a truly random design. I mean, if you're one that works.
Well, you know, so it depends what you mean by random, right? So, no, honestly, it turns out that random doesn't have like a unitary definition. So what's random? So the thing that I should have said instead of random is conditional entropy. So what's conditional entropy? So conditional entropy is one way of making operational a notion of randomness, or one notion of randomness. And that's the notion that the subject has no information available to them to predict what the next stimulus will be. Okay? Now, if I write down a particular M sequence, which is a sequence which actually has perfect conditional entropy, okay, there's no way that the subject can ever guess what the next trial will be based upon the trials that have already preceded. Okay, that's perfect conditional entropy. Now, there's an M sequence which provides this. Okay, now I've written down my M sequence, I have it on a piece of paper, and it is in no sense a completely randomly generated sequence because I've made it and I might use it over and over again. Okay, but it does fit this criteria of having perfect conditional entropy. So, but then what do you mean by randomness? Well, maybe you mean, well, I want to be random. It has to be something which is generated stochastically and can vary from occasion to occasion. Well, that's another notion of randomness. And it might be the case that that kind of randomness is important to you to avoid certain sort of confounds in your experiment. Because, of course, that notion of randomness is at the heart of the experimental method, right? Being able to randomize the assignment of treatments to different time points so that it cannot be the case that any kind of confound can affect it, right? Maybe it's rather unlikely, but maybe it's the case that the particular M sequence order I've picked is one that kind of gets to be generally known, and lots of people know this M sequence order, right? And at that point, then its conditional entropy drops to 0, because if everyone has memorized this particular M sequence, like suppose you're scanning a math PhD student who has memorized this M sequence, then they know what the next stimulus is going to be because they know the M sequence. Anyway, so it just goes to show that there's different ways of defining randomness from that standpoint. And conditional entropy is at least one useful operational definition for the kind of experiments we do, but it might not be the only one.
So would you use the same sequence for every subject in the study, or would you generate a unique sequence?
You could use the same sequence for every subject in the study, and that's often done. And I don't see anything especially wrong with it because these sequences do have this. The ways that could fail, right, or lead to a biased result or have some kind of problem seem fairly unlikely. I mean, it would have to be along the lines of, I happen to scan a group of math PhD students who knew the M sequence, right? It just seems very unlikely. But, I mean, some people might sleep better at night knowing, honestly, they might sleep better at night knowing that, like, their experiment is one where it is completely stochastic. It's random every one. But, of course, where are you going to get your random sequence from? You're going to use a computer to generate it? Well, that ain't so random. I mean, the truth is that there is no perfect solution to these kinds of things. But some people do feel more comfortable with using a different random sequence, right? So what you could do is, for example, have opt-seq give you the top 20 performing random sequences, okay? And then use those for your 20 subjects. And that's something that people will frequently do. And then randomly choose from among them, right? And, and cover your eyes while you do it. There's lots of different things that you could try and do to maximize randomness. But all right, so in any event, so that's sort of a couple of extremes of design. Just to kind of round these out, let me just also mention something called a sparse event-related design. So a sparse event-related design, you guys are already familiar with because it's the example that I keep drawing on the board, and that's one where you have a neural event, say, like every 16 seconds, and there's space such that your expectation is that the hemodynamic response function will be able to rise and fall completely during the time between one and the next. Okay, sparse event-related design. Why would you want to do a sparse event-related design? Well, in general, there isn't much call for it. The random designs have better power than a sparse event-related design. And if you're interested in measuring this precise shape of the hemodynamic response function, there's better ways of doing this too. The only time a sparse event-related design comes into comes into its own is under the following circumstances. When I've been talking about detection power so far, I've been talking about optimizing power for a given period of scanning. Like you got 1 hour on the scanner, you got your $400 that you scraped together from your piggy bank, you got 1 hour on the scanner, that's it, and then you want to collect as much data as you can during that time and optimize your power. Suppose it's the case that that's not your limitation, right? Your limitation is not the amount of scan time you have, but the number of stimuli you can present. Suppose, for example, you only have 20 stimuli. Like you've worked, for years to generate some stimuli which have some kind of manipulation of grammar and syntax or something else. And these are like the only 20 you can come up with, okay? At that point, a randomized event-related design is not the way to go. This kind of sparse design is going to maximize your ability to detect these things. You want to put each event separated by a good bit of time with a lot of time in between to get a good measure of the baseline and then present your next stimulus, okay? So when your limitation is the total number of stimuli you have, these kind of sparse event-related designs do better. Okay? All right. Any further questions about experimental design? Yes?
A limited number of different stimuli or total number of stimuli you can administer in a session?
The total number of stimuli you have, just total. So if adding up all the stimuli that you have, if you are limited in the total number of stimuli you have, such that the limitation is not the amount of time you have to scan, but the number of stimuli you have, then this kind of design is better. Does that answer your question, or try again what you're asking?
You have four conditions.
Okay.
And each condition can be 10 different dimensions.
Okay.
Okay. But not 20.
Right.
Is that the limitation you're talking about, or that you can administer a total of 100 events in a run?
Yeah. Well, let's see. It depends. It depends what you're trying to optimize. If you're trying to optimize, suppose you have 4 different sorts of stimuli, right? You've got flashes of blue light, flashes of red light, flashes of yellow light, and pictures of pages of the Dead Sea Scrolls, right? Imagine those are your 4 sets of stimuli, right? You got as many blue light, yellow light, and red light flashes as you want, but you only got 10 pages of the Dead Sea Scrolls, right? That's all you got, okay? If you're trying to maximize detection of neural activity evoked by presentation of pictures of the Dead Sea Scrolls, then you're going to want to take those 10 pictures and spread them out as much, because that's what's really limiting you there, okay? If, however, you are primarily interested in the blue, yellow, and red flashes, and for some psychotic reason you've included the pictures of the Dead Sea Scrolls, then at that point, then cram as many flashes of light as you can into the experiment, and then your limitation becomes the scanning time, not the number of stimuli you have. Okay. So let's see now. Oh, yeah, just one other last kind of design, which is kind of neat, is so I described event-related and blocked and all the rest. So, oh, yeah? Yeah. Good. Okay, great. Thanks for bringing that back up again. So if you use a random design, how do you know where to put your low-pass filter? This is kind of tough, right? So if here is now the power spectrum of your task, right? Low frequencies, high frequencies, amplitudes. So we talked about the case in which you have a blocked experimental design, right? And you've got the power of your task looks something like this, right? And you've got a 1/f noise function, which looks something like this, and you say, okay, well, when I go to filter the data, do that digital filtering, if you remember back to the beginning of our session, we said, well, just remove all this power at those frequencies below that lowest frequency of the experiment, right? Easy. Well, what if you have one of these random event-related designs? What's your power spectrum look like? Well, your power spectrum is going to look like something approaching this. Something approaching a flat line, right? And here comes the 1/f noise. The question now is, well, at what point should I kind of do the cutoff? How many low frequencies should I remove? Because each low frequency down here is carrying as much information about the task as any higher frequency up here. But these low frequencies are noisier than these high frequencies. The ugly answer is there is no one good answer. Okay, this is something that's screaming out for like a mathematician to come in and spend some time analyzing it and saying like, okay, well, here is the distribution of variance for your task, and here are the is the power spectrum of your noise, so here is the amount of filtering that would be optimal. Nobody's done it. Nobody's done it. So in general, what people end up doing is adopting just a general frequency cutoff. They take a look at the inflection point of their 1/f noise spectrum. They say, well, it really kind of turns the corner about here. So I'll just filter everything below there, assuming that that's an improvement. But you know what? I mean, that could definitely be improved upon. If someone wanted to spend the time to systematically evaluate how many low frequencies you would need to remove and how that affects this trade-off between removing noise yet also removing task variance, then that would be a great service to the neuroimaging community, but though somewhat tedious. But no one's done that yet. Yeah.
With the sparse event-related design, say you only have 20 trials,
Yeah.
how many subjects in general do you then have to run? You have to run more, right? Like that's the trade-off.
I can give you. She's saying how many subjects we have to run. So she's thinking about doing this Dead Sea Scroll experiment. I can tell. Don't take that from me. So if so she's thinking about how many subjects would you need in that kind of circumstance. So there are no hard and fast answers to these sorts of questions. It depends entirely upon the magnitude of the effect within subject. But let me just give you a general statement about power. Using a sparse event-related design and detecting button presses, thumb movements to press a button. Okay, if a subject performs 20 thumb presses, okay, you can detect from primary motor cortex those. This is back on our 1.5T GE scanner. Those 20 button presses could be detected with about 85% power. All right, so 85% of the time within a single subject, you could detect the neuronal activity from primary motor cortex from 20 button presses in a sparse event-related design. Okay, so that gives you kind of like a rough sense of the power that we're talking about here. So you would need to have. So if you have, and so I would call that sort of a strong effect, right? The effect of like making a motor act from primary motor cortex would have to be counted as a strong neuronal activity effect. And so it takes about 20 trials to get about 80% sensitivity within a single subject. So, power calculations are tough, but at least with that as a basis, it can give you some sense of where you need to go from there. All right? Yes?
Sort of related to the previous question, if you're using one of these, the random design, you've got obfuscop seek, say,
Yeah.
why wouldn't you tell it, so keeping the power spectrum for the HRF design,
Right.
why would you tell it, say, make it flat, but not make it flat from, say, 0 to nitrous, but 0 to some point that, I know is going to be thrown away by my HRF anyway?
Yeah, no, you could do that. So what you're doing is then you're losing randomness. You're losing conditional entropy at that point. Okay? You're saying, I'm going to now allow the subject to be able to theoretically have some information, right? Because the moment you move away from a flat power spectrum as your expectation, there starts to be some. But that's a perfect entree to the last thing I want to say in the last 2 minutes, and that is, so how about if that? How about if you're willing to accept some kind of predictability on the part of the subject, for the ordering of the experiments, but you want to do a little bit better in power, okay? Do you really need perfect conditional entropy to fool a subject into expecting that there's no pattern there? Or, subjects aren't that bright. I mean, maybe it's the case that you can have some randomness, that's enough to fool them. Well, this is the basis of what's called stochastic designs. And there's a paper that was written by Carl Friston and a guy named Eric Zarin, who was here as a graduate student some time ago. And it has to that's what they call these things, stochastic designs. So what's the idea of a stochastic design? So imagine you have two sorts of stimuli, bagels and donuts. And you have the probability for each period of time, on each trial, there's a probability of there either being a bagel stimulus or a donut stimulus, okay? And you can imagine it being, in a perfectly random design, 50-50, right? The chance of on any one trial there being a bagel stimulus or donut stimulus would be 50-50. But what you can imagine doing is maybe tweaking that probability over time. So imagine that for the first 30 seconds of the experiment, there is a 0.7 probability of bagel and a 0.3 probability of donut. And for the next 30 seconds, it's a 0.3 probability of bagel and a 0.7 probability of donut, okay? So if I start to graph this out as, with bagels and donuts here, I'll just draw the bagels for now. It might look like bagel, 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 and then bagel, 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 bagel. So it's the case that the density of bagel stimuli kind of increase over periods of time here, okay, and then decrease over other periods of time. And if you set these, it's the case, it must be the case that there is a setting for these proportions such that the subject would not be able to detect that there is that they're not perfectly 0.5, right? So obviously, if it's perfectly 0.5, they're not able to make any prediction. But maybe 0.51 or 0.52 or maybe 0.8 or 0.9. I mean, who knows? It might depend upon the circumstance of the experiment. But if you're willing to accept a little drop in this randomness, in fact, if you're willing to accept a 10% drop in conditional entropy, so things become 10% more predictable than perfectly random, that doubles your power. Okay? So that's a big change. It's a big change. So these stochastic designs are definitely worth looking into. So if you're in a situation where you're willing to accept a little bit of predictability on the part of the subject, then that can